Welcome to International Biorenewables Law and Policy. This presentation is part 3 of our three-part series on the economics of biotechnologies. We will complete this series by looking at a specific technology, fast pyrolysis, to understand the cost components of biofuel production. This slide here, prepared by Professor Robert Brown, showcases the various products that you can produce from a single fast pyrolysis biorefinery. If you start with agricultural residues such as corn stover, you can pyrolyze them, producing a gas, solid, and vapor product. The gases can be burnt as a natural gas substitute to provide process heat. That heat can be used to power the pyrolysis process. The solids, also known as biochar, can be utilized in different ways. They could be combusted because biochar can serve as a coal substitute, but its more promising use is in the use of activated carbon or as a soil amendment. By returning it to the soil, we can improve the quality of the soil as well as sequester carbon. The third product are vapors and aerosols, which you can condense into heavy ends and light ends. The heavy ends can be further separated into phenolic oligomers or pi sugars. To give you a frame of reference, the heavy ends here are what usually are called bio-oil. The phenolic oligomers can then be further upgraded into fuel oil, which can be burnt in boilers, or bioasphalt, which can be used to pave roads and pathways. The sugars can be refined into high-quality sugars and sold as a product, or fermented further into ethanol. In the light ends, we have several chemicals. One promising application of that light ends is to convert it into biocement, but you could also convert it into gel fuel for emerging markets. As you can see, there's a wide range of products that you can produce from the fast pyrolysis process, and it's this kind of diversity of products that is a strength and a challenge for biorefineries. It's a strength because you can address several markets, but it's a challenge because the values of these different products are not always high, and so you have to find market conditions that make it a viable alternative. Now we'll look specifically at how we use fast pyrolysis to produce biofuels and what the costs are associated with that process. In the case of biofuel production, you can look at the process as incorporating several steps. If you start from biomass, we have to pre-treat it, just as in many thermochemical processes. We dry it and we grind it. The pre-treated biomass can be sent to the fast pyrolysis unit, which again operates around 500 degrees Celsius. The vapors can be sent to a solid removal unit where we recover the biochar. And the remaining gases can be condensed into heavy oil or bio-oil. That bio-oil can be upgraded and eventually converted into transportation fuels. We're talking about gasoline and diesel that's compatible with existing vehicles. The non-condensable gases can be sent to the steam generation unit to provide heat for the process. And the light fraction, in this case, we're going to use it with natural gas to produce hydrogen, which we need to upgrade the oil. This process involves several steps, and so each of the steps contributes different capital and operating costs. We'll look at some of the major components of the economic analysis. We're going to make some general assumptions. The facility that we're considering in this analysis has a capacity of 2,000 metric tons of biomass flowing into the facility per day. We're going to make a generic assumption that the cost of that feedstock is $83 per metric ton, that the biochar is being sold as an energy product to produce heat or power, and it has a value of $20 per metric ton. Natural gas will use a market value of $260 per metric ton. The facility tries to achieve an internal rate of return of 10% and has a plant life of operation of 30 years. These assumptions are baseline assumptions recommended by the U.S. Department of Energy. They are designed to represent a typical biorefinery based on our experience with corn ethanol facilities. And so you'll see that many studies employ very similar assumptions. The capital cost for a 2,000 ton per day fast price facility is estimated at around $277 million. The big contributors to that cost are the pretreatment and pyrolysis sections. This includes the drying, grinding equipment, and the pyrolysis reactor itself. And so some of these equipments are fairly large, particularly the dryers, and so they contribute a significant portion of the cost. The second largest portion of the cost is the hydrogen generation. These are steam reforming units, which are fairly mature technologies, but they're usually employed in very large-scale refineries. When you build them at a small scale of 2,000 tons per day, the steam reformers and hydrogen generation units tend to be a significant portion of the cost. There are other sections here that contribute varying amounts of cost to the facility, but those are the main contributors as in this particular configuration. In addition to capital costs, we have several additional cost components. As we discussed earlier, feedstock cost is a major contributor to the overall cost of biofuel production. In this case, we're somewhere around the 20% range. In addition to fuel, capital cost is a significant portion, but capital cost here is broken down into several parts. The return on investment, which is the financing and the profit that you want to make out of that process, can be considered a type of capital cost. We also obviously have to pay income tax, and we have to pay for capital depreciation. So those three components together contribute about a third of the cost of the fuel. And then we have several other costs. We have the biochar credit shown at the very bottom. The biochar credit is relatively small because we're assuming a relatively low value for the biochar produced. Some researchers believe that the biochar, if used in agronomic farms, could have a much higher value. If there was a carbon price, we estimate that a carbon price would also contribute a significant revenue to the facility. One particular challenge with estimating the cost of advanced biofuels is that when you look at the mature cost estimates, they look fairly competitive. So when we compare it again here, biochemical gasification pyrolysis technologies, you can see that most costs range between $2 and $5 per gallon of gasoline equivalent. If you look at the historic price for gasoline, at least in the US, it's typically ranged between $1 and $4 per gallon. So you may wonder, at $4 per gallon, why aren't some of these technologies already commercially available? Well, the challenge is that when you build a facility for the first time, you're going to encounter much higher costs than the estimates for a mature design. We've done some pioneer cost analysis which allows you to estimate what that premium on that first facility will be. What this chart shows is in blue dots the estimates for what the mature end plant design cost estimate is, and the range of possible values for facilities that will be built today based on that design. For example, in the biochemical case, we estimate that a mature commercial plant would produce biofuel about $5 a gallon. However, if you built that facility today, that facility will produce the biofuel at a price of somewhere between $7 and $11 per gallon. A lot of this premium is driven by the high capital cost of building a facility. Pyrolysis, as we've shown before, has a lower capital cost estimate. And so based on that lower capital cost estimate, the projections for a pioneer plant can be as low as $4 to $8 per gallon, or even $2 to $4 per gallon. Another driver for the high cost of these biorefineries is that when you build them at 2,000 tons per day, for many of these technologies, that capacity is just too small to take advantage of what we call economies of scale. The notion of economies of scale is that as you build larger and larger facilities, the cost per unit per product actually decreases. That's what's shown in the purple line indicated as capital. Biorefineries are unique in that when you build large facilities, you have to bring in feedstock from longer distances, and that's going to increase your cost. And so when you break down the cost in terms of the capital cost and the delivery cost of the feedstocks and other materials, what you find is that there's going to be an optimal capacity indicated in the total here. Ideally, you want to build your facility near that optimal size in order to capture the benefits of economies of scale without having to pay too much to bring the materials into the facility. Another issue that impacts the cost of biofuels is that the first designs or the pioneer plants do not take advantage of improvements in construction and engineering of the facilities. This is sometimes called learning. When you look at other industries, such as the gas to liquids, coal to liquids industries, you'll see that for the same or similar type facilities, they have been able to reduce their costs over time. In the case of the gas to liquids, some of the initial plants had cost as high as 200,000 US dollars per barrel per day of capacity. Over time, they've decreased it to almost half. Coal to liquids has seen a modest decrease, but it's still a significant amount. In the case of biomass to liquids, if we were to assume that a similar amount of learning would occur to the industry, after building 1,000 facilities, which is not impossible considering that many of these biomass to liquids facilities could be smaller sized than the large facilities, you can see that the projections just from learning rates would reduce the cost of these facilities from over $200,000 a barrel per day to close to $30,000 a barrel per day. Now that seems like a very low capital cost, but when you compare it to other industries, the corn ethanol industry, for example, has reduced their capital costs from $70,000 per barrel per day to below $20,000 a barrel per day. That is almost as low as building an oil refinery, which costs about $15,000 per barrel per day capacity. So this is the importance of understanding that the cost today for biofuels are not necessarily the cost that they would have if they were to be adopted widely. In a study done by our group, we combined the impacts of economies of scale and learning rates to estimate how the two economic impacts could reduce the cost of biofuel production. This slide shows a comparison of gasification and fast pyrolysis based on different learning curves to understand how the cost would be reduced. The takeaway from this slide is that, for example, if you start at the very top with the blue circles, you can see that the impact of economies of scale suggests that you should build a gasification facility at a plant capacity of about 75 million gallons per year. If you allow the technology to improve after building several units, maybe 100 units, maybe 1,000 units, that cost could be reduced to somewhere in the $2 to $3 per gallon range. Not only do we reduce the cost, but we can actually build larger optimal scale facilities. In the case of fast pyrolysis, we have a similar effect. Learning reduces the cost of the biofuel significantly, but interestingly, in the case of fast pyrolysis, it actually allows us to build even smaller facilities, somewhere in the 20 to 25 million gallons per year capacity. That suggests to us that different technologies might evolve in different pathways. Some will suggest that we build larger facilities, but some might progress by building smaller distributed facilities over time. To summarize, advanced biofuels are currently expensive to produce due to several techno-economic factors such as feedstock cost and capital cost. Capital costs in particular for these small-scale emerging biorefineries are several times higher than for mature facilities. This includes the conceptual design of these biorefineries, as well as their competitors in the coal, gas, and petroleum industries. However, by building these biorefineries at their optimal scale and allowing the technology to evolve, we could reduce their cost over time. This concludes our three-part series on the economics of biotechnologies. I encourage you to read through the readings to get a better appreciation of the details related to the cost of producing biofuels.